Hello students, welcome to today's session. So today we will be discussing problem solving on acid radicals. So we are into the session number 3. Session 1 and 2 of salt analysis were on to the topic of segregation of acid radicals. Let us do some problems. These problems are more than one choice questions which are meant specially for upcoming IIT advanced paper. So here are the questions. Hope you would appreciate the work which I am placing in front of. All these questions are very interesting and really will strengthen your acid radicals. So here comes the first question. In this first question, they said there are two acid radicals X and Y. X, when treated with zinc in the presence of acidic condition, produces a gas, and same gas is being produced by acid radical Y on acidification with dilute HCl. And that gas in particular is colorless and is having a foul smell, or it is having some noxious smell. And that gas, when treated with moist lead acetate and moist lead cadmium acetate, gives particular black and yellow precipitates. So this is the data is being given to us. Now here you have to see the things very carefully, because here zinc is being mentioned wherever, whether it is organic or inorganic. When zinc is being mentioned somewhere, it generally acts as a reducing agent. It has the property of acting as a reducing agent. And if it is acting as a reducing agent, so this, in a way, this anionic species must be oxidizing anion. This must be a oxidizing anion. Okay, that oxidizing anion reacting with zinc, producing a gas. That is the point which you have to keep it in mind. Now coming on to the options availability, we almost have all the oxy anions of sulfur and along with the sulfide ion. So what I can do here is, let me place some discussion in front of you, because in one question we are going to address many things. So sulfide, when on acidification, gives you sulfurous acid, which is a thermally unstable protonic acid which easily can decompose and produce a SO2 gas. Same is with the thiosulfate ion. It also would give you this thiosulfuric acid, which on heating decomposes to water, sulfur dioxide and sulfur get precipitated. And this in particular gives you H2S gas. Now the point here is, what we have to see into this SO2 and H2S, both of these are having dirty smell. This in particular has rotten egg-like smell, which is not soothing to us, and this is having a smell of burning sulfur. Smell like burning sulfur. Burning sulfur is just like a when you ignite some tire, the soot or the smell which you happen to see from that burning tire, because that vulcanized rubber is there which is having sulfur, so that produces a SO2 gas. Now the fact of the matter is, they haven't told us anything about the particular type of smell. They haven't written. They wrote a foul smell. So this means the examiner is wanting us to identify whether it is H2S or SO2. This is what they have said. And second thing is, as they have treated it with zinc, so this particular sulfite ion, which is in +4 oxidation state, can go to sulfate, which is in +6 oxidation state. When it happens to go from this side to this side, it primarily be acting as a reducing agent. So most of the time we have seen sulfite ion to act as a reducing agent, like sulfite ion changes to sulfate ion when treated with KMnO4 or any oxidizing agent, Cr2O7, something like this, dichromate ion. But definitely it can also change into sulfide ion. If I happen to take this as an oxidizing agent, just like in the case of zinc must be acting as a reducing agent, and this would change into sulfide ion. It can have that property as well, because it can go both ways. But as regard to thiosulfate ion, which is in +2 oxidation state, it has primarily been seen that in the case of thiosulfate ion, it either would change into tetrathionate ion, where the sulfur is in +2.5 oxidation state, or sulfate ion, where it is in +6 oxidation state. I mean to say, this happen in a bit of acidic medium, and this is in alkaline medium. So in both cases it is acting as a reducing agent. So thiosulfate ion, most of the time it is acting as a what I should say, as a reducing agent. On to the contrary, as regard to the sulfide ion, Sulfide can go to, you know, sulfur zero oxidation state, or sulfite ion or sulfate ion, where it can be in definitely sulfur cannot go to lower negative oxidation state. It definitely can move on to the upper oxidation state, 0 or +4 or +6. In all of these, this would be acting as a reducing agent. So what we have sensed out from this particular discussion is that the species which is reacting with zinc must be sulfite ion, because these two are reducing agents. So let us now I think we have almost done the question. So what basically we can say here is, if X is sulfite ion, say for example, if I take it as sulfite ion, so this can produce H2S gas, and that H2S gas can also be produced from the sulfide ion. And this H2S, when treated with moist lead acetate in the moist form, H2S will give some sulfide ions, because the solubility product of cadmium and lead is very less as sulfide, so they require very less amount of sulfide ions. So this get precipitated and this also get precipitated. So almost we are done with the question. So let us see what are the options available. X is thiosulfite, this is wrong. Y is sulfite, Y is sulfite, no, this is wrong. Y is sulfite, this is correct, and this is correct. Here one more thing I should add here, just into your knowledge bank. Whenever you would see what I would say, zinc and H positive, zinc in OH negative is also a reducing agent. So this in particular is quite important, which I should want you to mark it. Sulfite, this radical when treated with zinc changes it to H2S, and itself definitely would change into Zn2 positive. But when you would treat nitrate ion, this is very important, nitrate ion in alkaline condition with zinc, it reduces it to ammonia, and it itself change into this particular soluble complex, where zinc happens to be again in the +2 oxidation state. So it went from +5 to -3. So make it a point, zinc in alkaline condition changes, because we are talking about the acid radical. So I'm showing you vis-a-vis in comparison that this zinc is used where and where. So zinc can reduce sulfite to H2S as well as nitrate to ammonia. This you always have to remember. Or another reducing agent can be aluminium in presence of alkaline condition, can also be used to reduce nitrate to ammonia. And here I do mark one more thing into your knowledge bank. You can also take nitrite ion. Nitrite ion also changes to ammonia in the presence of these two reducing agent. And just to see the balancing part, I have shown it to you. Just after the session, you just see into it. The discussion is in front of you. So this is reducing agent. Balancing, you can do it yourself. So it is quite easy as regard to the balancing part. Moving on to the second question. Second question again is a very interesting one, where you are being given 6 anions or 6 acid radicals are being given to you. First they have treated it with AgNO3. First they have treated it with AgNO3 and you got a residue and filtrate. The residue number 1 is then treated with dilute HCl and you get residue 2 and filtrate 2, and then it is being treated with a silver nitrate and ammonia to give you residue number 3. So here, before I go into the option, let me show you what they have done. So first they have treated this with silver nitrate. So they treated it with silver nitrate. So as a consequence, you would get filtrate and you also would get residue. Now this we have done many times. Earlier I also have said in the last session 1 and session 2 that silver nitrate is such a good precipitating reagent. This almost precipitate all the anions, mostly all the anions of the acid radical. Now these on precipitation you would get silver sulfide, sulfite and silver phosphate along with silver chloride, bromide and iodide. So these are the all these get precipitated, and thereafter they have added into this dilute HCl. Now make it a point, after the silver nitrate addition they added the dilute HCl. So that means the solution has now become acidic. In the acidic solution, I already have said many times in the session 1 and session 2 that Ag2S and the silver chloride, bromide, iodide would not dissolve in the acidic medium. So they will come out as precipitate. So this would be the residue number 2 which they are referring to. This is residue number 1. And in the filtrate 2, what we shall be getting here is sulfite ion and phosphate ion. These two would be available here. Now what is the discussion about it? This we have done in the previous session 2 also, that if I just would give you a bit of idea. So silver sulfite, when put into acidic medium, what you would get is this thing, and this sulfite ion has the tendency to take up H positive from the acidic, because HCl is being added, to change into H2SO3, which is a thermally weak, thermally unstable protonic acid, and this would change into this thing. Since there is a evolution of SO2 gas, so this SO2 evolution would shift this equilibrium forward, this also to the forward, and this also to the forward. So this solid get dissolved in the acidic medium. And same viewpoint we can take, such similar type of a viewpoint we can also take for the silver phosphate also. So silver phosphate would break into this, and this phosphate ion is a conjugate base of a weak acid. This is a weak acid. This is a weak acid, and this is a conjugate. So this eagerly would change into this side. So if this equilibrium would move to this side, this also would move to this side. So this also get dissolved into it. Now the fact of the matter here is that you should be asking me, what about silver halides? When AgCl is being done the same way, Cl negative, now this is poorly basic. It is poorly basic because it's a conjugate base of a very strong acid, that is HCl. HCl, Cl negative, H positive, this Cl negative comes here and it picks the H positive. But HCl is a strong acid, so it would shift the equilibrium this side. So this would go backward. Or you can say it through the, if AgCl is put into HCl, it's a common ion effect as well. But if it had been a case of AgBr, same viewpoint you can take it here, Ag positive, Br negative, and Br negative would not like to accept H positive to change into HBr. This would not be going forward. In fact, this is backward driven. So this also is a backward. So this would remain solid, this would remain solid. So this discussion I already have done many times in the previous sessions as well. So this means these get precipitated, and for Ag2S I already have did the discussion. So go into the session 2 where this has been discussed in detail, as well as in session 1 also. So the point here is this would come in the filtrate, and the interesting part is when you add ammonia to this again, if you just would add ammonia being ammonium hydroxide is a base, as soon as the solution becomes neutral, and if you add a bit of silver nitrate more, these two get precipitated again. So this is the beauty of the qualitative analysis in terms of the acid radical, that as I said, anion radical segregation happens with the properties, 3 properties: acid base behavior, precipitating reagent, and the third one which we have discussed in length is the redox property. So these are the 3 things which would work. So first they added AgNO3, residue came, they allow it such a way that they found that these 4 would not precipitate, these would precipitate, and then again they precipitated in the neutral medium. So what I'm trying to say is that leaving aside these 4 silver salts, most of the silver salts, when precipitated in neutral medium, they all get precipitated. These also, if these are there, because in the starting the solution was neutral, they also get precipitated. All the anions get precipitated as silver salt in the neutral medium, but in the acidic medium these 4 ions would not dissolve. So this is very important, always keep it in mind. Now coming on to the options. So filtrate 1 has no anion. This is perfectly written. This would not have any anion. So we did not find any anion. No anion here. In the filtrate one, there was no anion. Okay, moving on to the next one. Residue 3 is, okay, what was residue 3? This was this one. So residue 2 was containing phosphate ion and sulfite ion, if you could remember. So these two get precipitated. So this statement is also correct one. And residue 2 is of AgBr, AgCl, AgI, AgA. So this is also correct. This we have just spoken that Ag2S, AgCl, AgBr and AgI got precipitated. Filtrate 2 has 2 radicals. Filtrate 2, whereas yes, it is having 2 radicals. Yes, this also is a correct one. So in this particular question, the answer would be A, B, C, D. So this is a typically important question to remember with. So coming on to the next problem. Select the correct statement. This is a factual question. Let us see how many of you could do it. So AgCl soluble in ammonium hydroxide, hypo and in KCl. This is a question being asked to you. AgF is soluble in water. AgBr is not soluble in acid and dissolves in KC and hypo. And all these three are soluble in hypo. So this question is also very interesting. So first fact of the matter is AgF, the solubility of AgF in water is the maximum one. So this is perfectly right. B option is perfectly correct. And AgCl is soluble in ammonium hydroxide. This this again is a in hypo and KC, this is perfectly right. AgBr is not soluble in nitric acid. This we have just done, that AgBr, AgCl, AgI would not be soluble in acidic medium and dissolve. So I think all the options are correct. Let me show you the discussion here. So solubility in water is correct. AgF is maximum soluble, and all of these would not be as soluble as AgF is. And solubility of all of these in ammonia in special, here I should mark that there are two compounds, AgI and Ag2S. These would not be soluble in, not insoluble in ammonia. These two are insoluble in ammonia. Always remember, or ammonium hydroxide. So this would, I should have written it AgI here. So this is AgI. So this is insoluble, and these would be considered as soluble. In hypo and KC and in nitric acid in acidic medium, none of these is soluble. So this is insoluble, and wherever you have hypo or KCN or NaCN, there they will make this water soluble complexes, so they are soluble. So make this point, make this as a chart and keep it in your study table, because this is a quite it seems like easy, but it's a typically important question. You have to see the options very religiously. First is correct, second is correct. AgBr is not soluble in nitric acid, perfectly right. Dissolves in these two, perfectly right. AgCl, AgBr all are soluble in hypo is also perfectly correct. Okay, moving on to the next question. So detection of SO2 gas can be done by, now SO2 gas can act as reducing as well as an oxidizing agent, and when is being treated with any oxidizing agent, it tend to behave like a reducing agent, because sulfur is in +4 oxidation state. It happens to go to the sulfate ion, which is in +6 oxidation state. Now the point here is, and along with the corresponding species of the oxidizing anion. Now, although this question seems like easy, but it is not so easy. You have to be little vigilant, because they have said detection of SO2 gas. Because SO2 gas in itself is colorless. It is colorless. So it is colorless. Since it is colorless, so it is to be treated with such an oxidizing agent which would show some color change. Then only you can detect it, otherwise would not be able to detect it. What I am trying to say here is, KMnO4 is purple color. When you treat it with SO2, it changes to Mn2 positive, which is colorless or light pink. And K2Cr2 orange, it happens to go to green Cr3 positive. Bromine is brown colored, and it changes to Br negative, which is colorless. But hydrogen peroxide in itself is colorless. SO2 is also colorless. And if it changes to sulfate ion, which is also colorless, and this goes from -1 to water, it in -2, this also is colorless. So H2O2 would not be able to show you any sort of color change. If you are not able to see any color change, we would not be able to detect it. So are you getting my point? So I think I wrote it here. Purple to colorless or light pink, orange to green, brown to colorless. But when you treat H2O2, which this SO2 is also colorless, and all the species are here also colorless, so this H2O2 would not be able to detect it. So the answer to this question, although the question was easy, but have to be seen very carefully. So detection of any gas with the oxidizing agent would be seen when you would see some observable color change in oxidizing anion. If the starting gas is colorless, then this has to be always adopted with. So the answer to this question would be ABC. Okay, fair enough. Moving on to the next question. So in the next question, what they have said, oh, beautiful question it is. Sulfite ion treated with oxidizing agent, okay, changes to sulfate, and then PR stands for precipitating reagent, where it got precipitated with some barium salt or calcium salt as barium sulfate or calcium sulfate. Or first you add precipitating reagent and then add oxidizing agent. Okay, now you have to identify the incorrect statement. So what basically we are doing is, so first you added some oxidizing agent where sulfur went from +4 to +6. And then you added some M2 positive. That M2 positive can be Ba2 positive, let's say barium sulfate get precipitated. Or you first added barium 2 positive here, so that this barium sulfite is being produced, and then you added an oxidizing agent where it goes from +4 to +6. Okay, now what the options are asking us? Options are saying salt 1 dissolves in acid. This is salt 1. Whereas salt 2 do not. Okay, fair enough. Oxidizing agent can be lead acetate. Lead here is in +2 oxidation state. Had it been lead 4 positive, lead 4 positive salts are oxidizing because of the inert pair effect. Lead 4 want to go to lead 2 positive due to inert pair effect. But lead acetate would not be acting as an oxidizing agent. In fact, it is a precipitating reagent. So this option seems like incorrect. Precipitating reagent can be barium chloride. This is perfectly right. Salt 2 will dissolve in acid, whereas, okay, so primarily we are left with A and D option. So here again the same point. This will dissolve in acid. Because as soon as you add acid to this will change into M2 positive SO3 negative, and SO3 negative would pick 2H positive and change into H2SO3, which on heating would change into sulfur dioxide. As soon as sulfur dioxide leaves the reaction mixture, this equilibrium gets shifted towards this side, and as a consequence this metal sulfate get solubilized or dissolved into the acid. But when you talk of M2 positive and sulfate is poorly basic. This is, or other way around, it is a conjugate base of a strong acid which would not want to take up H positive, so it would not dissolve. So make it a point, I am referring once again, salt of a or conjugate base of a weak acid. If you have a salt of a conjugate base of a weak acid, it dissolves in a strong acid. So this will not dissolve. So what option did we get here is, so one answer is C option was correct. Salt 1 dissolves in acid. This is a wrong statement. And salt 2 will dissolve in acid. Metal sulfite will dissolve and salt 2 will not. So C and D would be the right answer for this particular question. Okay, moving ahead. There is a salt P when treated with dilute HCl produces a colorless gas which turns orange colored dichromate to green. So this seems like easy, because dichromate, if you want to change into chromium 3 positive, that is green, there must be, this is an oxidizing agent, so there must be some gas which would be reducing in nature, a gas which would be reducing in nature, any gas which can act as a reducing agent. So here the point is that what are the options available? Almost all the oxygen ions of sulfur and sulfide ion. So sulfide, sulfite, sulfate and thiosulfate. So if you add H positive into it, so this gives you H2S, which can act as a reducing agent, and this on H positive gives you H2SO3 and then produces SO2. SO2 can also act as a reducing agent because it can act as oxidizing as well as better act as a reducing agent. And similarly, this would change into H2SO4. No, H2SO4 is in sulfur is in +6 oxidation state. It want to come down. It only act as an oxidizing agent. And here you have H2, so this also would turn to water, SO2 and sulfur. So here we are able to understand fact that H2S and SO2, those species which are producing these two would, because this a reducing agent and this can also act as a reducing agent. So answer to this question shall be then it would be either sulfide ion, thiosulfite ion or this. So it would be ABD. ABD should be the answer to this particular question. Moving on to the next question. A salt P when treated with dilute HCl produces colorless, odorless gas. As soon as you see colorless, odorless gas, definitely it would be coming from carbonate or bicarbonate, because carbonate or bicarbonate, by taking H positive, they change into carbonic acid. This takes 2H positive, this take 1H positive, and this then change into carbon dioxide and water. And carbon dioxide is a colorless, odorless gas. But now the point here is both of these are given to us, and the aqueous solution of P turns phenolphthalein pink. P must be having, okay. So this is to be done very carefully, because it is more, as I am saying, all these questions are more than one choice. So here the things become difficult, because both of these would produce colorless, odorless carbon dioxide. But the point here is you need to take into consideration aqueous solution of P. So this we know in the last session also I told you, when you have carbonate and bicarbonate and you want to distinguish it, just take the salt and put that into water and add phenolphthalein into it. If the phenolphthalein turns pink, it means it is carbonate ion. It is carbonate ion, because carbonate ion is more basic. Hydrolysis of carbonate would happen more rapidly as compared to bicarbonate. Bicarbonate also do okay, let me do it here. Let me write it once more for you. So what I am referring here is this is bicarbonate. When you put this into water, it produces this along with OH negative, and as you know, KH is equal to KW upon Ka, and here HCO3 negative, H water gives you H2CO3 plus OH negative. Both of these solutions make the solution basic, but the fact is weaker this acid, more is the KH. So this acid is weaker than this. If I write acidity of bicarbonate ion is lesser than carbonic acid. So this acid is weaker, so Ka is less, so KH is more. If KH is more, that means more hydrolysis is happening, so making the solution more basic. So in the more, although both the solutions are basic, this is slightly greater than 7, but this is almost greater than 9 or 10. So the pH greater than 9-10 make the phenolphthalein pink. So here the answer we will take it as carbonate. If phenolphthalein had not been mentioned, then we would have gone for carbonate and bicarbonate. Okay, moving on to the next question. Salt P dilute HCl gives you colorless, odorless gas. Colorless, odorless gas again seems like carbonate or bicarbonate. Aqueous cuprous chloride. Aqueous cuprous chloride is being added to give you green colored precipitate. Green colored precipitate. So the fact here is again the same viewpoint. Carbonate and bicarbonate definitely on addition of H positive would produce carbonic acid, and which would produce carbon dioxide. Okay, so that means these two can be possible. But when you add some precipitating reagent to it, carbonate and bicarbonate, so make it a point, bicarbonate is always water soluble. When you add precipitating, no reaction. But that for carbonate, just like in this case, when you add cupric chloride, this cupric carbonate along with cupric hydroxide, this is a basic carbonate. This is said as to be basic carbonate. Cupric chloride, when treated with the carbonate, this get precipitated as green precipitate. So this is also called as basic carbonate. So this always have to keep it in mind. Just like zinc carbonate happens to get precipitated with zinc hydroxide. Same is with, I think, mercury carbonate along with HgO. So these are considered to be basic carbonate. So what option they have given us? Let me see into the option. We are almost done with the question. P must be carbonate. This seems like perfectly correct. Okay, they haven't given us any option of bicarbonate. P must be sulfite, wrong. R must be basic carbonate. Yes, R is basic carbonate and Q is color. So this seems like a easy question, not a tough one. A, C, D, where only you have to see into consideration the C option. Moving on to the next option, next question. Salt P with dilute HCl, gas with dirty smell, okay, and salt P turns yellow colored ferric chloride to light green. Yellow colored ferric chloride to light green. So that means FeCl3, where Fe is in +3, happens to go to Fe2 positive. So this means this is acting as an oxidizing agent. So there must be some reducing agent or a anion which would have a reducing nature, or a radical which would produce a gas which is of a reducing nature. Anion which would on acidification would produce some gas which can now do the reduction of ferric ions. So let us see what option they have given. So it turns, okay, salt P turns ferric chloride solution to light green. So what option do we get here? So either, because it is in +4, this is also in +4, it can go both way, reducing, oxidizing. It is in +6, so this would not be there, because this can only undergo reduction. This is a oxidizing anion, and this is in +4, this would not do any sort of redox. So the answer to this question would be either A or B, because both of these would produce dirty smell on dilute HCl. Okay, moving on to the next question. Which may be used as an reagent to distinguish bicarbonate from carbonate salt, or bicarbonate carbonate salts are to be distinguished? When such question happens to come in the paper, one of the anion should react with the reagent, other should not. If that is the case, if both start reacting, we would not be able to distinguish, or both are not reacting, then also we are not. So this we have done few minutes back. Phenolphthalein is a way of identifying the carbonate, perfectly right. And this would not get precipitated with any precipitating reagent. So all of these are precipitating reagent. So here you would get silver carbonate, here you would get barium carbonate, here you would get lead carbonate. So the fact of the matter is that all the 4 options we can choose to distinguish carbonate from the bicarbonate, because all these would react with the carbonate ion. So that is the important question. Moving ahead, so I almost have made lot of questions, but for today's session, I think let us do few more. Okay, which among the following salt of silver is or are not soluble in ammonia? So this we have just few minutes back, I told you categorically that this particular salt and these would not solubilize in ammonia. So the B and C is the answer for this question. And moving ahead, this again seems like an interesting question, that if you heat them together, so this I would mark it as homework. Try this at your place. I would address this in the next session. I just would give you this as an question to be solved by you people. So this again, oh, this out of the way, I have placed some other question. Acidic oxide existing as a giant molecule. So all of these seems like acidic. This also is acidic. All of these are acidic in a way, but this and this would behave, because this is a very important question in a way. Giant molecule existing as a giant molecule, because it is available in a 3D structure. This also is available in a 3D structure, and when you treat them with water, they will make the system hydrolyze with water. They will make the acidic thing, boric acid and salicylic acid you would get with.